In this video, we look at a couple more examples involving the mean value theorem. And in these two particular examples, we're dealing with functions that have infinite discontinuities in the interval of interest. So the problem statement says, determine whether the mean value theorem applies. If so, find the x values guaranteed to exist by the theorem. And then if not, can you modify the problem statement so that the theorem does apply? If so, do so and illustrate your result graphically. Now remember what the mean value theorem says. It says that if f is continuous on the interval from a to b, so that's what one of the things that we're looking for is continuity, and differentiable on the interval from a to b, then there exists at least one x value on the open interval from a to b, actually, such that the derivative at that x value is equal to this expression. And the derivative, remember, is the instantaneous rate of change of the function. And this expression actually represents the average rate of change of the function on the interval of interest. So basically our theorem says that if the function is continuous and differentiable on an interval, we can always find a point on that interval where the instantaneous rate of change equals the average rate of change. And there might actually be more than one, but we're guaranteed at least one, provided that the function is continuous and differentiable. So let's look at this function. We've got y equals cosine of x plus tangent of x, and we're on the interval from 0 to pi. Now remember that tangent of x is actually a quotient. It's defined to be sine of x divided by cosine of x. There's my pen. Looking for my black pen, I couldn't find it for a second. Now, since this tangent of x is actually sine of x divided by cosine of x, y is going to have an infinite discontinuity anytime that cosine of x is 0 and the sine of x is non-zero. Since sine of x and cosine of x are never 0 at the same time, this expression will always be undefined whenever cosine of x equals 0. This function has infinite discontinuities, or we can say it has vertical asymptotes, every time the cosine function is 0. And the cosine function is equal to 0 at all of the odd multiples of pi over 2. So x will equal pi over 2 times an odd number. If n is an integer, if I take it and double it, it's going to be even. If I add 1, then it'll be odd. So this is for x equals this, where n is some integer. Okay, so we ask ourselves, is this function differentiable and continuous on the interval from 0 to pi? Well, no, pi over 2 is on that interval. So our function is going to have an infinite discontinuity at x equals pi over 2. That just happens to be one of these vertical asymptotes. So we'll say y is continuous and differentiable on its domain, but it has an infinite discontinuity at x equals pi over 2, which is in the interval of interest. That means the mean value theorem does not apply. We say, okay, when does it apply? Well, I think it would apply as long as our function is continuous and differentiable and it doesn't have an infinite discontinuity. So anytime we're on an interval that starts at one of these odd multiples of pi over 2 and ends at the next odd multiple of pi over 2, then the mean value theorem would apply. So that's how we can modify the problem statement. We'll just choose some interval from a to b, such that a to b, this interval, closed interval from a to b, lies entirely inside some multiple or some interval starting at one odd multiple of pi over 2, and then ending at the next odd multiple of pi over 2. That's one odd number, and then that's the next odd number. If n is equal to 1, or excuse me, if n is equal to 0, we're just going to look for an interval from negative pi over 2 to pi over 2, and then we'll just choose an interval that's a finite interval, including the bounds that is inside that interval from negative pi over 2 to pi over 2. Okay, let's look at the function graphically on desmos.com. Then we'll have a better sense of what's going on, and then we can discuss more about the mean value theorem. Okay, so here's our function, y equals cosine of x plus tangent of x. I made it a dotted line because I'm not talking about the entire function. I'm only talking about that part of the function on the interval from a to b, where a is 0 and b is pi. So we're actually interested in just this green part of the function. If I plot the points a f of a and b f of b, then we see those two points there on our graph. Now, the mean value theorem says that if the function is continuous and differentiable on an interval of interest, then we can always find a point, at least one point, where the instantaneous rate of change is equal to the average rate of change. Now, if we look at this function on this interval, we see obviously we're going to have a problem because the function isn't continuous. We've got this infinite discontinuity at x equals pi over 2. If I wanted to draw the secant line, the line that's passing through the 2 points, it would look like this. And that's just a line with a negative slope, right? If we look at the calculated secant or slope of the secant line using Desmos, it's approximately negative 0.637. So that's our slope. Now the question is, well, is there any x value on the interval from 0 to pi such that the instantaneous rate of change equals the average rate of change? Well, since the mean value theorem doesn't apply, we don't know. I mean, there might be a point that has the right slope, or there might not be a point that has the right slope. So we can explore that visually by graphing some tangent lines on the interval from 0 to pi. And notice what happens as x increases between 0 and pi. All of those slopes are positive. Actually, it would be easier to see that they're positive if we, undo that. Just have Desmos evaluate the slope for us. So this is the slope at x equals x naught. And as we increase x from 0 to pi, that slope is just getting increasingly positive. It gets more and more positive as we approach pi over 2. The slope is 600 when x equals 1.53, which is very close to pi over 2 because, you know, pi over 2 is like about 3.14 divided by 2, right? So that's very, very large. And then eventually it skips to the other side. And then we've got a bunch of other slopes. All positive, they're decreasing now. But still, the slopes are positive. So slopes are positive the whole time. There's no way that we can get a slope that is equal to that slope of the secant, which is that negative 0.637. And again, that's because of the particular function that we're looking at, but also, well, in this case, the mean value theorem doesn't apply. So the mean value theorem says that if the function is differentiable and continuous, we're guaranteed a point where that slope is the slope of the tangent line is equal to the slope of the secant. If the mean value theorem doesn't apply, that means that might be true or it might not. Well, in this case, it's not true. There aren't any x values that give us the right slope. All the slopes are positive, and the slope of the secant line is negative. So you might say, okay, I'm a math teacher, and I'm writing textbook problems or problems for my students, and I say, is there any way I can modify this problem so that the resulting problem, so that it has is there any way that I can modify this problem so that the mean value theorem does apply? Well, yeah, I need the function to be continuous and differentiable. So that just means I need an interval that is nested inside an interval from one odd multiple of pi over 2 to another odd multiple of pi over 2. So we can't include any of those vertical asymptotes. I already said this when we wrote it down in the paper. But now let's get rid of that equation of the secant line. Actually, no, or I want to keep the equation of the secant line. Let's let A equal negative pi over 2 and B equal pi over 2. Now we're talking about just that branch of the function. Now the function is undefined at both of those values. X equals negative pi over 2 looks like this. So that's another one of our asymptotes. But as long as I stay on this branch, or if I stayed on this branch or this branch or this branch, my mean value theorem would apply. But I need my A and B values actually not to be the equations of those asymptotes. I need them to be values in the interval from negative pi over 2 to pi over 2. So I think what I'm going to do is I'm going to change this, is add a slider for A. And I want the lower bound to be negative pi over 2 and the upper bound to be pi over 2. And for my B value, I want it to go from, see, I'm adding a slider for B now. I want my B value to be greater than A every time, and I want it to be less than pi over 2. So if my A value is over here at, let's say, negative 1.4, and my B value is there at B equals 1, then we've got a secant line that looks like that. And then that interval from negative 1.4 to 1 is nested inside that interval from negative pi over 2 to pi over 2. So we're good to go. The mean value theorem does apply. The function is nice and differentiable and continuous on the interval. So we will be able to find some x value between x equals negative 1.4 and x equals 1, such that the derivative of the function is equal to the slope of the tangent line, or the slope of the, or excuse me, the slope of the tangent line is equal to the slope of the secant line. And this white line that's graphed right now is the secant line. So the slope of the secant line is 3.22 approximately, 3.219. And we've got that graphed right here. Now for my slope of the tangent line, we're going to use f prime. And I don't think I've already typed that somewhere in here, but it might be sort of farther along in the book, or in the, I'm calling it a notebook, but it's not, it's just Desmos graph. Still got Mathematica jargon in my brain. So when I'm looking for the equation of the tangent line, the derivative is going to give me that slope. So the derivative of cosine of x plus tangent of x is negative sine of x, is the derivative of cosine, plus the derivative of tangent, which is secant squared x. And then we're on the interval from A to B. And then the equation of the tangent line will be y equals the original y value, so y evaluated at that x value, plus the slope at that x value, which is just the derivative at that x value, times x minus x naught. Now I want my x naught values to lie between A and B. And then we'll just try to find one that gives us sort of the right slope. Let's compare f prime, the secant. So I'm looking for f prime at x naught to equal the slope of the secant. So I'll just move my slider until that happens. Hard to get it exactly right. It's somewhere in there between negative 8.9, 8.87, negative 8.2. And say, how can I do this? What's an easier way? Well, one thing that we could do is we could take the derivative function and then graph it. And then we could also graph y equals the slope of the secant line. And then when we have those equal to each other, when those two functions are equal to each other, those x coordinates of the points of intersection would correspond to the x values where the derivative is, or the derivative at that point is the same as the slope of the secant line on the interval from a to b. So let's do that. So we have y equals cosine of x plus tangent of x on the interval from a to b. And I actually want to use the same a to b that I used in this one. So I've got a is negative 1.2 and b is 1.2. Oops. No, wait, that's not right. I have a is negative 1.4 and b is 1. So this purple graph is the graph of the derivative. Now, the slope of the secant line is still given by this formula, and that's approximately that 3.219. So you say, okay, well, where is this derivative equal to the slope of the secant? It's just the point of intersection of those two curves. So it's that point right there. Notice that the y value is 3.219, which is what we want. That's the slope of the secant. And the corresponding x value is negative 0.878. Zero 0.878. So let's plot the point negative 0.878 and f evaluated at negative 0.878. And then graph the tangent line there. And we can see just from our graph that the slope of the secant line and the slope of the secant line, which is the slope of this white line, and the slope of the tangent line at negative 0.878, that's one of these orange lines, is the same because those two lines are parallel to each other. I said is the same, are the same, excuse me. Let me get rid of that other orange line. Here we go. If I type in x naught equals negative 0.878, we see that that is equal to that, and we look at f prime evaluated at that x value and the slope of the secant evaluated at that x value. They're not exactly the same, but they're close. We've got an approximation of the point of intersection of those two curves out to 3 decimal places. So we're going to say that that's good enough for us. That line looks like it's parallel to that line. So we're good to go. Now we can do that for various intervals. If we change the values of a and b, let's say we go from negative 1.5 to 1. And actually, let's change some of our settings here. Let's let x go from negative 5 to 5. Maybe negative pi to 5. So it's a little bit easier to see what's going on. And maybe let's let b go out to 1.5. So we had a little bit more symmetry there. Now the slope of the secant is negative or 9.4-ish approximately. And the question is, well, when is f prime evaluated, or when is f prime equal to that 9.4? Well, the function is nice and smooth and continuous on the interval from negative 1.5 to positive 1.5. So if we want to, we can plot a point on the graph. And we can plot the tangent line there, or sketch the tangent line there, excuse me. And try to find the x values that cause that function, or cause that tangent line to be parallel to this white secant line. I'm just going to move my slider. I want my slope to be 9.4. So approximately negative 1.22. And I think that there might be one on the other side as well. It's a little bit hard to do. Looks like 1.25-ish over there, but again, that's 9.10 or 9.11 versus 9.40. So it's not exactly right. If we want to, we could always graph the derivative and that slope of the secant. And again, the x values that we chose were negative 1.5 to positive 1.5. So those are our A and B. So we've got that. In that case, we actually have two x values. The slope of the secant there is 9.4, 9.401 approximately. And we have at x equals negative 1.22 and x equals 1.255. Our slope, or the derivative function, is equal to the slope of the secant. So we get two answers just from reading the graph. And if we let x1 equal negative 1.22, let's let x2 equal 1.255. And then we'll evaluate f prime at each of those x values. And we see that the derivative at those x values is very close to the slope of the secant there. Of course, we were just using a numerical approximation. And we've got a tangent line drawn at x2. I'd also like to have a tangent line drawn at x1. So let's plot this point. So that we can see it. And we'll say y equals f evaluated at x1 plus f sub prime, or f prime at x1 times x minus x1. And I think we can see that those lines are parallel to each other. All right, so that's it. That's how we handle it. The function does not, or the mean value theorem does not actually apply to the function as it was originally, or the problem as it was originally stated. We had cosine of x plus tangent of x as our function on the interval from 0 to pi. But if we change that interval so that it does not include any odd multiple of pi over 2, then we're good to go. As long as we are between odd multiples of pi over 2, we're going to be on a single branch of that cosine of x plus tangent of x function. And as long as we're on a single branch, that function is continuous, it's differentiable, and therefore the mean value theorem applies, which means there's at least one x value where the instantaneous rate of change is equal to the average rate of change on the interval. The next problem is very similar. We've got a function on an interval, and we also have an issue with an infinite discontinuity. So I've got a rational function. Rational functions are well-defined on their domain. They're continuous, they're smooth, they're differentiable. And as long as the x value, or excuse me, as long as the denominator is non-zero, then we're fine. Then the function is continuous. Now, if we're looking at this function on the interval from -3 to 0, we're going to have a problem because the denominator is 0 and x equals -2. So this rational function has an asymptote. X equals -2. And because the degree of the numerator and denominator are the same, it also has a horizontal asymptote. Y equals the ratio of the leading coefficients, which in this case is 1. And we're interested in this function on the interval from -3, which is to the left of our vertical asymptote, to 0, which is over here. When x is equal to 0, y equals 1.5, so we're actually up here. And when x equals, let's say 1, we get 4 divided by 3. So 1 1/3. Something like that. Did I do that arithmetic correctly? I think I did. And then when x equals -3, we get a 0. You might be saying to yourself, okay, well, does this function, or does the mean value theorem apply to this function on this interval? The answer is no. Y equals x plus 3 divided by x plus 2 has an infinite discontinuity. At x equals -2, which is in the interval from -3 to 0. So the mean value theorem does not apply. But if I take any interval that does not include x equals -2, the mean value theorem should apply. So if I want to modify the problem so that the mean value theorem applies, I just pick an interval that excludes -2. So I can choose an interval where a and b are both greater than -2, or I can choose an interval where a and b are both less than -2, and either one is fine. So in part B, we have an interval where x starts at -1 and it goes to 5. So the mean value theorem will apply in the second interval. So we'll say since -2 is not in the interval from -1 to 5, and y equals f of x is a rational function, the mean value theorem applies. Okay. Now, if we want to, we can sort of think about what the graph looks like. We can take the limit as x approaches -2 from the left and the right, and think about how the function behaves near -2. We can think about what happens as x goes to positive or negative infinity. Obviously, the y values approach 1. But I think it's easier to see if we graph it online. So let's go on online. Let's go to Desmos and look at what this graph looks like. Look at the graph online. I said, look at what the graph looks like. You know what I mean. All right, so here's our function. And we said it has a horizontal asymptote y equals 1 and a vertical asymptote x equals -2. So I've sketched those. Those are the white dotted lines. And then if I'm thinking about the entire function, I would just graph that. But I'm not actually interested in the whole thing. I'm only interested in the interval from A to B, where A is initially 3 or -3 and B is initially 0. So I'm going to make this a dotted line because I'm not interested in the whole thing. And then we'll just take that part where the x values are between -3 and 0. So when we look at the graph now, we can see that it has 2 branches. It has 2 parts. We've got one part between -3 and -2, and then another part between -2 and 0. So the mean value theorem doesn't apply, as we discussed. Now, if I were to sketch the secant line at those points, sorry about that. The slope of the secant through these 2 points is 0.5. A line actually looks like that. And the question is, well, is there any x value where the slope of the tangent line is equal to the slope of the secant? Well, since the mean value theorem doesn't apply, there might be an x value where that's true, or there might not be an x value where that's true. But if we look at the curve, we can tell that this function is decreasing. So all this secant or all the tangent lines are going to have negative slopes here, and this line actually has a positive slope. So I don't think that there's any way we're going to get a tangent line that is parallel to the secant, which is what we need, what we're looking for. We can see that visually if we compute f prime. And we can compute that just using the quotient rule. We've got f is equal to x plus 3, that quantity divided by x plus 2. So if I'm taking the derivative of that, I'm going to have, if my function value, my function is this, we use the quotient rule. So we say low, that's the bottom function, times the derivative of the top function, which is 1, low d high, minus high, it's x plus 3, d low, derivative of the bottom function is 1, all divided by the bottom function squared. And if you distribute that negative through the second set of parentheses and then collect like terms, the x is reduced, and then you just have a 2 minus 3, which is a -1. And so we get this. And the denominator doesn't simplify. So we do that calculation. Usually I would do it on paper, but we just typed it instead. So that's our derivative. And then if I want to sketch a tangent line, that tangent line would be y equals the original y value, the y value at x equals x naught, plus the derivative evaluated at x naught, that's our slope, times x minus x naught. So we've got change in y divided by change in x, times change in x gives us change in y plus the original y value gives us our new y value. And now we're going to let our x values, our x naught values, range between a and b. They're giving me a hard time now. Not plotting the lines. I guess I also need to plot the point. Oh, actually, I already wrote that down here. There we go. But there's a point. Sort of an unfortunate. So we look at all these tangent lines and they all have negative slopes. We can tell that they're going to be negative slopes as well because we look at the form of f prime and it's -1 times 1 over something that's always positive. So we see that the slope is always going to be positive and the secant line is always, or the secant line between these 2 points has a positive slope. If you wanted to see that more explicitly, you could always evaluate f prime at x naught, and Desmos will do the calculating for you. So as you move your slider around, you can see how the derivative changes. So you have a slope of -1, and then it gets steeper and steeper. So larger and larger in magnitude, but increasingly negative. And then it goes the other way. At one point, it's undefined. That's when x equals -2. And then we just keep going. So you say, okay, the theorem doesn't apply in the original interval, so we can modify it. Now, as long as our interval does not include -2, we're going to be fine because rational functions are continuous and they're differentiable. as long as you don't include any of those x values that correspond to zeros in the denominator that are not zeros of the numerator, or in other words, the vertical asymptotes of the function. Now, if the numerator and denominator are both zero, then you actually have a discontinuity. So the theorem wouldn't apply there either, but the limit would exist. You could make the function continuous by redefining the function at that point. But in any case, if you've got the denominator is zero and the numerator is not zero, that corresponds to a vertical asymptote, and the theorem does not apply. Now, if we change the interval from -1 to 5, so that starts here at x equals -1 and goes all the way over here to x equals 5, the function is nice and continuous. So let's do that. So let my a be -1 instead of 3, and let my b be 5. And I want to get rid of that tangent line for a second. There's our secant line. We zoom in a little bit. That's the interval we're interested in. Our y is between, looks like 1 and 2 approximately. So I'm just going to change the window a little bit to make it easier to see. But our y value is going to 4. So that's that part of the graph that we're interested in. And this sort of teal line is our secant line. And we're looking for an x value on the interval where the derivative is equal to the slope of the secant line, or the slope of the tangent line is equal to the slope of the secant line, or if you want, the instantaneous rate of change of the function is equal to the average rate of change of the function on the interval of interest. You can do this visually by plotting a point. We've got this -0.02 as one of our points, 1.505. Draw a tangent line there. And then we can just move the slider until we try to find the appropriate x value. I'm looking for that tangent line to be parallel to the teal line. And it looks like at approximately 0.7, x equals 0.7, that tangent line is parallel to the secant line. Say, well, how can I find that without just moving sliders around and just sort of eyeballing it? Isn't there a better way? Well, of course, we could just take the equation for f prime, set it equal to the slope of the secant line, and then compute the x value. So we'll do that. I've already done that here. I've got the x values on our graph, but we'll do that by hand. We'll confirm that that's the answer, and then we'll substitute into the Desmos to confirm our answer visually. One thing I noticed when I was looking at the graph is that I substituted x equals 1 and plotted the point at x equals -1. That point should not be there. It should be this one right here. So the graph actually kind of looks like this. I'm not doing a very good job with my graph. And then that's the whole graph. And the part that we're interested in now for part B is the part where x starts at -1 and y ends and ends at 5. So we're talking about this part of the graph. And we're looking for the x value on that interval where the instantaneous rate of change equals the average rate of change. So let's do that. First, we'll compute the slope of the secant. Well, it's going to be the y value at x equals 5 minus the y value at -1 divided by 5 minus -1. Just do some calculations. F of 5 is 5 plus 3 divided by 5 plus 2, or 8/7. And then we'll subtract f of -1. So of -1 plus 3 divided by -1 plus 2. So we get 2 divided by 1, which is just 2. And then 5 minus the -1 is the same as 5 plus 1, which is 6. Now I need a common denominator. So I'll write that 2 as itself over 1, multiply by 7 over 7 to get a common denominator in the numerator of the larger fraction. So I end up with 8 minus 14, which is -6 divided by 7, all divided by 6. So -6/7 times 1/6 is dividing by 6 is the same as multiplying by 1/6. we get a negative 1/7 as the slope of the secant line. Say, okay, I want the x value on the interval from -1 to 5 that gives me this slope of the secant line. Well, I can find that by first computing f prime. So that's the derivative with respect to x of this x plus 3 divided by x plus 2. And we've already done this. We typed it in on the computer, but we can do it again. The derivative of a quotient is the bottom function times the derivative of the top function. The mnemonic is low d high minus high d low. And we say, whenever we say d low, we just mean the derivative of the bottom function. The d is an operator that applies to the function in front of it. All divided by low low. And of course, this derivative is 1. This derivative is 1. So we end up with that x plus 2 minus the quantity x plus 3, all divided by x plus 2 quantity squared. You distribute the negative. We've already talked through all of this. The x is reduced, and you end up with -1 divided by x plus 1 or x plus 2 quantity squared. So that's our slope all the time. At any x value, except for x equals -2. This is going to give us the slope of the curve at that particular location. We're looking for the locations that give us a slope of -1/7. So we set f prime equal to the slope of the secant and just solve for x. So we've got -1 divided by the quantity x plus 2 squared equals -1/7. The only way that happens is if those denominators are equal. So we must have x plus 2 squared equals 7. To get rid of the squaring function, to undo that, we take the square root of both sides. Don't forget your plus or minus on the right. And you've got x plus 2 equals plus or minus the square root of 7. And then when we subtract 2 from both sides, we get x equals -2 plus or minus the square root of 7. Now, that corresponds to two values, of course. X equals -2 minus the square root of 7. And x equals, I guess we probably should say or x equals -2 plus the square root of 7. And I don't actually know what those values are, but I can use a calculator or Desmos to find numerical approximations. So now we've got x equals -2 plus the square root of 7 is this 0.645 approximately, calling that x1. And x equals -2 minus the square root of 7 is this -4.646 approximately. Now, the one of those that's on our interval of interest is this positive one. This -4-ish number is way over here. And that's not on the branch that we're interested in. The branch that we're interested in is this branch on the right. And we're not interested in the whole branch. We're just interested in that part where x is between -1 and 5. So we're over here. We say, so that means the x value that we're interested in is x1 rather than the x2. And if we evaluate f prime at x1 and x2, we get -1/7 in both cases, which is good. We wanted the derivative to be equal to the slope of the secant line, and it is. We can just confirm that. The slope of the secant is, in the form of a fraction, is -1/7. So the slopes are what they're supposed to be. And we've plotted the point. Oops. Actually, this is the one that -0.7 is the one that I just got from eyeballing it. Is that right? Oh, that's f prime. The actual value of x1 is 0.646. 0.646 versus 0.7. I think, visually I got close enough. But if the exact answer is this -2 plus the square root of 7, let's get rid of the one where we were just approximating. Let's plot the point where the solution is. That's the x value where the slope of the secant or the slope of the tangent equals the slope of the secant. And the equation of the tangent line there is f evaluated at x1. That's our original y value plus the change in y over change in x. Times x minus x1, which is the change in x. So we can see that those are parallel to each other. Now the other point, we zoom out a little bit. It doesn't count. It's not on our interval. But you might still be thinking about it. You say, okay, well, what's actually happening over there? Well, at x2, we've got a point here. Plot that point. If there were a tangent line there, if that were on our interval of interest, it would be y equals the y value there plus the derivative at that x value minus times the quantity x minus that x value. And see, that tangent line is also parallel to the secant line. So this is not the solution we're looking for because it's not on the interval of interest. But it is another point where the derivative is equal to what we wanted it to be. So you have to ignore that one. The one that we're looking for is actually this one that's on our interval. But we see that there might be other points out there that are outside the interval. So be careful about that. Make sure you intentionally exclude those x values that aren't on the interval of interest. It's tempting to include them though, because they've got the right slope, they have the right values. But the mean value theorem deals with x values that are on a particular interval. All right, so that's it. In the next video, we'll look at another example. I think in that case, our function actually has a cusp. But let me know if you have any questions.